people are going to probably come in and watch after the fact as well, due to the change in the time zone. So I will, once we get started, we'll start in just a minute, and I'll introduce both of you, and then I'm going to go on mute and turn my video off, and I'll be sort of, checking in and out. And the tutorial's scheduled to last for how long?
2.5 hours with a break in between.
I think they have 2.5 for the total time, or maybe a bit longer. But they can then have, Cindy, you can organize maybe in the middle. You want a break somewhere, and then you can stop in there.
That's fine. Yeah.
Okay, I mute myself, and then you can get the start.
Okay. All right. We'll get started then. So. Hi, welcome to this tutorial. My name is Tim Oates, and I am going to introduce the speakers, and then we'll get started. So we have two people who are presenting. The first one is Sanjay Tripathi. She's currently a postdoctoral research at the Department of Anesthesiology at Washington University School of Medicine, where she's working on fairness aspects of using electronic medical records to design clinical prediction models. She received her PhD from EOR, IIT Bombay, writing her thesis on learning in the presence of label noise and feature subset selection. In addition to working on fair learning models and transfer learning, she keeps an eye on neat and pragmatic solutions to the label noise problem. Her co-presenter is Nandyala Hemachandra. He's a professor at the Industrial Engineering and Operations Research Center in IIT Bombay as well. And his current research interests include operations research methodologies such as machine learning, including reinforcement learning, neural networks, and Markov decision models, queuing models, and game theory. And he looks at application areas including communication networks, supply chains, financial engineering, logistics, and power systems. So I'll hand it over to you. I'm assuming that you're willing to entertain questions as this tutorial goes along. So I would encourage people who are listening to, just sort of speak up and interrupt with questions, and hopefully there'll be some good discussion at the end as well. All right, thank you.
Okay then, yeah.
So, morning all, I'm Sandhya, and I'll be presenting this tutorial along with my PhD advisor, Professor Hemachandra. So, I'll just share my screen. So today's topic is label noise, some problems and solution. So the outline is like this. We'll introduce the label noise problem, and then we'll go one by one to various methods which are used in classification as techniques like empirical risk minimization, then some deep neural networks, and then we'll go beyond 0-1 loss-based classification. And finally, we'll end with some experimental protocols and how do you induce noise and what next from here. So to start with, what is binary classification? You can just see like there are some pictures and then they are labeled as cats and dogs, and you have to predict for a new label whether it is a cat's picture or a dog's picture. Now in this binary classification, if you have somebody who is intentionally intentionally tagging a dog as a cat or a cat as a dog, or somebody doesn't know whether is not able to identify whether it is a cat or a dog, like in this case. So these labels are incorrect, and learning from these labels become problem because your classifier or your learner won't have will probably fit very well on the training data, but when you have to deploy it or when you have to test it out, its performance or its generalization won't be that good. So some sources where label noise can be seen are like in medicine, when there are X-ray images and it's very expensive to get them labeled by the experts. So there could be a chance of label noise there, or adversarial adversarial noise, somebody intentionally adding noise, or crowdsourcing because the experts are not doesn't have enough expertise, sensor noise. If a sensor fails, the labels or the data it was passing could just go hayway. And yeah, and many more such situations can be there where label noise problems can arise. So to start with, let's see what is the ERM terminology. ERM here is empirical risk minimization. So we'll have a joint distribution D over X and Y, where X is the script X is the feature space, script Y is the label space. And we'll start with binary classification, where the labels take binary values, that is -1 and 1. And then later on we'll move on to a multi-class case also, where the Y can belong to a set. Now here, for the first important thing to define here is eta, that's the in-class probability. It basically says what is the probability of a label being 1 for a given data point. And then pi, which is probability y equal to 1, also known as class prior. The goal is to find a decision function f from the feature space to a real number, and then the final prediction is done by thresholding this function f at 0 in case of binary classification. Script H is the hypothesis class of all possible measurable functions. Script linear is the class of linear hypothesis. So in ideal situation, what would happen is you would have a 0-1 loss function, which basically says which basically assigns a loss of 1 if your prediction and the true label doesn't match. Otherwise, it assigns a loss of 0. So that's what the indicator here represents, and it's denoted by L01. Now, if you have the whole distribution, you would want to compute the loss of that particular class over the whole distribution, and then this is called the true risk of the classifier F, and denoted by RD. So the minimizer, and you would want this loss to be minimum. The minimizer of this particular loss, true risk with respect to 0-1 loss function, is called base classifier, or base classifier's prediction, denoted by sign of 2 eta minus 1. Now, in real world, you don't have access to all possible samples from the distribution. So you only have a training sample S of size M. And in that case, what you do is you perform empirical risk minimization. That is, instead of you replace this expectation by summation here and try to find the minimum value of this R hat. Now, if you see this L, in case of 0-1, this turns out to be a NP hat problem. It's difficult to optimize this. So there are solutions like surrogate loss functions, which are generally an upper bound to the 0-1 loss. So this is the ERM terminology. Now, if you move ahead to label noise, what happens here is you see the label earlier was +1 -1. Now when the noise is induced, that is, it is flipped, it could be again +1 -1, but it is now denoted by D tilde. And the only sample which you are available with is S tilde, which is basically the set of all the data points like xi, yi tilde, and it's called corrupted data. The noise rate is basically the flipping probability, or the probability that given the true label was y, the flipped label is -y. And eta tilde x here, by simple calculation, you can easily find that eta x is a function of this noise rate, and eta tilde x is the function of this noise rate here, rho, and then original eta x. So if noisy, true L risk is denoted by RD tilde, and it's minimizer by F tilde star L. It's similar to the original or clean label case. We would have an empirical noisy case also, which is denoted by R hat D tilde. Now, what do you mean by, like, when you say that, okay, there is label noise, what can we do about it? So one way, or the ideal thing which we would want is to get a loss function or a classifier which is robust to this noise. That is, it is not affected by the label noise in the training sample, and generalizes well on the test data. So the noise tolerance under risk minimization is defined as given in equation 1. This basically says that the true risk of a classifier learned on corrupted data and a classifier learned on clean data is equal. So in expectation, if the risk of these two classifiers learned on clean and corrupted data is equal, then that loss function is said to be noise tolerant. Depending upon noise, we'll say whether the noise whether whether the algorithm is like how good is the algorithm, depending upon what type of noise it is robust to. So the noise models we'll talk about is, first is an easiest one or a general one. It's called symmetric label noise. It basically, where the flipping probability is a constant rho, and it's same for both classes. As you can see, if whether this y could be +1 -1, and corrupted in class probability has a simplified form here, that it is a linear function or affine function of the original true clean eta, and the class marginal also has the same form. In the class conditional noise model, your flipping probability depends upon the original class, that is y. So here you will see rho plus and rho minus. And corrupted in class probability has a has again a linear function, but then this term here is rho minus, which will create problems later. We'll see it. The third class of, or the most restricted class of noise models is instance dependent noise, where in addition to the noise depending on your labels, it depends upon the feature vector also, that is x. So here we have two subcategories again, label and instance dependence noise, that is rho yx. The noise rate is rho yx, and purely instance dependent noise. So the noise rate won't depend upon the label, but it will only depend upon the x. So the goal here is to to find a classifier such that when you test it on the data from clean distribution, it should generalize well. Yeah. So now I would hand over to Professor Hemachandra. He'll take over from here. So.
Yeah. So the first, yeah, just give me a minute. Yeah, just give me a minute. I will just download this fellow. Yeah, is it visible?
Yes.
Oh, just give me a minute. Yeah, sorry about it. Just give me a minute. While talking to you in the beginning of this, I was trying to download this, and the presentation started.
Shall I keep sharing? I can move the slides for you.
Yeah, maybe that is better. Actually, I wanted to avoid that. But anyway, let us start. It is getting delayed here. Can you do that?
Yeah. You'll have to stop here. Yeah. So you can start.
Yeah. So the first comment I want to just make is that while particularly writing about or preparing for this tutorial, in general, there is no clean way of bifurcating or organizing the entire area. There are two ways of doing it. Down the line, we will see that we will pick up topics based on this combination. One is the performance criteria. As Sanjay said, that this is the criteria that is designed, that is for the designed classifier that is to be tested in a test set. So for most part of it, it will be the 0-1 loss or the accuracy using this loss function, as was mentioned earlier. Then at some point of time, we will move on to what is called cost sensitive learning criteria or alpha weighted 0-1 loss function using the alpha weighted 0-1 loss function. One reason is that there are many data sets primarily which are actually unbalanced data sets or imbalanced data sets, and intrinsically the domain of application is such that actually some type of misclassification is more important than the other type of misclassification. The primary motivations being like transactions and in an online transactions are including the financial transactions. How does one detect fraudulent versus normal transactions? By nature, the fraudulent transactions are generally much low in number, or the data is imbalanced in some sense. That is one aspect to it. The other more important aspect probably is that it is important in some sense to prevent a possible fraudulent transaction rather than trying to block once in a while through a normal transactions. Both are actually errors in some sense. But one particular type of error, when a particular a normal transaction is actually by mistake is thought about as a fraudulent transaction, that may not be that worrisome. But if a fraudulent transaction goes through because the classifier or the online mechanism felt it as a normal transaction, then it leads to a lot of troubles. So these are classical examples of what are called cost sensitive criteria. So other area where it normally occurs is actually in the medicine in some sense. Yeah, I mean, from a radiologist or somebody would like to say that based on the setup, it is important to say that in a diseased person is not a diseased person is not viewed as diseased. That is that if that error occurs, that is quite a worrisome error, rather than unwittingly or unknowingly giving some medication to a normal person because it is viewed as a diseased person. Yeah. Hello. Okay. So this is what is called, this leads to the what is called cost sensitive criteria. And this is usually denoted by alpha weighted 0-1 loss function as well. Then we will try to go particularly in the multi-class things, 3 or more classes, the cross entropy criteria. And there are various ways of actually looking at a performance criteria, including arithmetic mean, which are very popular in some setups. We'll come to it a bit later. This is one way to think about various models. The other way to think about is actually the nature of classification. What is the problem? What is the nature of the binary classification here? I mean, what is the nature of the underlying classification problem? The popular one is, of course, binary classes. And this itself will have what is called, as she mentioned earlier, Sanja mentioned about symmetric label noises, where the notation would be rho, class conditional noise models, CCN models, rho plus and rho minus, that is the noise rates, and the instance dependent noise model, rho x. Then a good part of it will also try to do it what is called multi-class noise models. And there are various other ways of maybe weak learning, weakly supervised learning, and that type of related models. So along the way, we will try to make it wherever it is important, we'll try to highlight it, these combinations. The point I'm trying to make here is that the label noise problems have various combinations. We will be doing actually binary classification with a 0-1 accuracy as the target. we will try to look at that type of problem, or we'll be looking at the multi-class noise models with the cross entropy setup as a criteria, because that will be the KL divergence between the etas that she mentioned earlier. So various combinations actually will occur here. We'll try to make it as much as clear. This is what we meant by this particular slide called various models. The general thing I want to just mention is that this is so vast area, and actually in general developing at a very fairly fast rate. It is clear that we may not be able to complete complete or even touch upon many of the important papers that might have occurred, that may have appeared, or even archive papers. Just want to mention that any such missing bias is actually not obviously not intentional. Either it is because primarily it is oversight, one reason. Other reason is actually that probably we don't have much time to think about it, and rather completing this tutorial, 2.5 hour tutorial or something like that. These are the two primary reasons. We will be willing to talk about if the audience has some comments along these lines. All right. Okay, so we'll get into some details here. Yeah. So one of the first ones we want to talk first earliest, which we believe actually is that a very sound result is due to this Professor Padapat Sastry and Naresh Manwani. I believe this is actually part of Naresh Manwani's PhD thesis. Yeah. So this particular reference is actually a review chapter they have written in a book on pattern recognition and classification problems. So here are the various ways of addressing the problem of label noise. One is to actually to restore the corrupted labels, or otherwise what is called cleaning the noise. This is actually quite laborious and tedious process, definitely. And the other one is actually is that if there is a way to think about and identify what are the clearly the noisy data points, they can be just pruned out from the data set that one has, whatever may be the type of label noise it is, and then you will get really what is called a clean data set essentially. Of course, this is also very tedious procedure, and it's quite, and both as the earlier one as well as this could be of course error prone as well, because it depends upon the person who is doing this activity, and one may not be able to identify noisy points, or even the correct labels may not be able to identify it to be restored. In binary setup, it may be clear. If it is one label is known to be very sure that it is noisy label, then you can easily flip it. But if it is a multi-class, it is not clean how to flip it. You know, what is the meaning of restoring the noisy data points labels? And then there are other schemes which actually target and minimize the effect of label noises. And the other one, which actually that will be the most focus of this particular tutorial, is actually what is called designing noise tolerant algorithms. That is, take the noisy data as it is and use a suitable algorithm to design a classifier which actually will have an accuracy, as was mentioned in the previous slide. What is the goal of this? Generally, the goal of this label noise problem is actually design a classifier using the corrupted label data sets as a training data, and that should have an accuracy which actually would be same as the accuracy of a classifier that would have been obtained by hypothetically clean data. Whatever was mentioned in the previous accuracies being clean, one way to think about is that imagine hypothetically that there is a clean data is available, and one can design an algorithm using that clean data, hypothetical clean data, and that will have some accuracy. The label noise problem essentially says that that accuracy should be matched by an algorithm which actually uses the noisy data but still achieves the type of accuracies. Essentially, that is what it is. So then this will be the focus of the good part of our tutorial here. Then one can design these classifiers using loss functions, particularly in the empirical risk minimization type of setup. And how to identify these loss functions which are actually do the job, or how to modify them and get the job done is the general theme of this entire tutorial. At least that, and actually that is the general theme of the entire area, and definitely it will be the theme and focus of our tutorial today. So okay, some parts of it actually we didn't mention it here explicitly. This label noise problem is actually quite old, some 30-35 years actually sort of old. There was a revival in this area due to primarily around 2010 by an interesting paper by Phil Long and Rico Servillo, who basically argued that by explicit computations, illustrated that certain loss functions are not label noise robust. This is one particular paper, and down the line also one particular loss function they emphasized is actually what they call convex potentials. Those who are familiar with this ensemble models will recognize that the convex potential or the convex loss function is the fundamental guy who drives the entire the adaptive boosting algorithm, where the entire rounds of the boosting are actually done by using the convex potentials or convex loss function. So surprisingly, this convex loss function, which is actually very good surrogate and one of the well-known convex surrogates function, the 0-1 loss, and is classification calibrated, is susceptible to label noise. That is a summary of this Phil Long and Rico Servillo's 2010 paper, which increased, which we believe about in the last 10 years, there is a phenomenal and explosive amount of work in this label noise, primarily because of this particular paper. That is our view. And then we can illustrate, we will not go into some details. Primarily, Naresh Manwani, Pedapat Sastry, and Aritra Ghosh, and some of these people and some other people have argued and illustrated by suitable counterexamples that some loss functions are actually are not robust against the SLN. SLN is symmetric label noise, the simplest of the noise models. If you recall, actually the SLN is the simplest of the noise models because there is a constant, in the binary class setup, there is a constant row, unknown of course, essentially unknown row, which actually flips the labels of any class, no matter what the data point X is, the data point feature point X is. That is the simplest model. So it turns out actually that many of these good, very good convex loss functions, which are actually classification calibrated as well, they are susceptible to are not robust against the simplest of the loss functions. So the one is actually squared loss if one is sticking to linear classifiers. And the other one is the very popular hinge loss that goes into the design of all the classical support vector machines. And the other one is exponential loss, which is similar to what I mentioned, Phil Long and Rico Servillo's starting point, and the log loss. So these are the some known functions which are actually convex surrogates to the 0-1 loss function and still susceptible to the basic and very elementary noise label noise model, the symmetric label noise models, symmetric loss label noise, SLN. Sometimes we'll use the SLN, sometimes you'll use the word or phrase called uniform noise, which is also very popular. Then in the face of this bunch of sort of negative results, Naresh Manwani and Pedapat Sastry in 2013 gave a positive result, which basically said that there are some loss functions actually which are actually robust to the SLN setup. And the two popular ones are actually the good old 0-1 loss function itself for any measurable functions, and the squared loss. When one restricts one, the design algorithm should restrict itself to linear classifiers. In other words, if one restricts oneself to the linear classifiers, the squared loss is actually is noise robust, as opposed to this counterexample. The counterexample in the which we mentioned in the previous here actually is the case one can construct for the squared loss function when the classifier is nonlinear essentially. But if one uses the quadratic loss function and sticks only to the linear classifiers, it actually is noise robust, SLN robust. So that is a summary of this type of particular paper. We will try to spend some time understanding the details of this this particular thing and some more details of this particular elementary, fundamental. We believe that actually this is a fundamental result, which I, first of all, for one reason, it is actually a first positive result in some sense. And the subsequent papers by essentially students working with Professor Sastry actually got some insight into what exactly is happening there. We'll keep revisiting to that type of other particular papers down the line. But in the time being, we'll just move on to the this particular result here. Okay, yeah. So essentially there, what they did is actually is that it is not that, one way to understand this entire positive results is actually that they were able to identify a sufficient condition on the loss function to be robust to the symmetric label noise. That is the summary. So, okay, our notation would be if given a loss function L, and suppose the loss function is denoted by bivariate argument f of x comma 1, when 1 is the label plus 1, that will denote it by L subscript 1 f, and similarly L minus 1 f would be the same creature evaluated at the negative label. If the essentially let us decompose, in quote unquote, decompose the loss based on the class label essentially. Then their sufficient condition is actually is that if the sum of these two components of this loss function is constant, for some k, then that loss function is actually is SLN robust. So in that sense, this is sufficient condition. If the loss function has this as property that no matter what the data point is, the loss at plus 1 by class 1 and the loss at the for the negatively labeled class, if this sums up to constant, then that particular loss function is actually SLN robust. That is the sufficient condition that they argued about. That is the sufficient condition that is given in this Aritra Ghosh et al. Paper. So this is a paper, as you can see, is a bit a follow-up to the earlier paper, which identified a lot of loss functions by Naresh Manwani and Professor Sastry, that a lot of loss functions are not robust. So this particular paper has a first positive result, and I believe this is an interesting result. Then by using the sufficient conditions, one can identify actually a bunch of loss functions which are actually noise robust to the simplest noise model. Of course, the 0-1 loss function does that because it adds up to 1, the k is equal to 1. More non-obvious loss functions are actually the novel unhinged loss due to Benjamin Van Roonen, Bob Williamson, and et al. The unhinged is actually is that just remove the max operator in the hinge definition, essentially 1 minus y into fx. So in the margin representation, these are just a straight line. Yx is the representation, so it will be actually here a straight line. So the hinge, as you recall, actually is a hinge on the x-axis at 0.1. It is a piecewise linear, whereas this is a still full straight line. Then the sigmoid loss function also has this property that it can add up to k, and the ramp loss and probit loss. So these are the loss functions actually which satisfy these sufficient conditions, and hence are noise robust when the noise label noise regime is actually the simple label noise, the rho. All right. So one observation is actually is that these loss functions doesn't need any noise rates. Actually, they are sort of agnostic to the noise rates. So the earlier methods I alluded to in the previous things, that one can denoise it or remove the data points, they're actually in one way or another way actually are noise rate dependent, whereas these are actually agnostic to the noise rates. We'll try to we'll see that actually down the line sometimes. This observation or idea that one is agnostic to the noise rates actually is quite important. And particularly it is like this in a very simple setting, is that suppose the noise is actually corrupted by adversary, then this property is useful because you are not your so-called response to this adversarial noise via loss function of this nature is not depending upon the noise rate. That means that you imagine that is a two-player type of game. The adversary is corrupting the labels, and you are trying to design as another player in this game, where you are trying to design a classifier which is immune to the noise rates, immune to the label noise problem. Then this particular condition or use of these loss functions will mean essentially that you will have a sort of dominant strategy. No matter what the level of noise is, as long as it is an SLN setup, you will have a uniform dominant good strategy, good response to it. you will essentially, I hope I'm clear, we can use any of these loss functions and you are agnostic to the noise rates. That's a summary. All right, so this is a fundamental idea, and then we'll move on to what is called class conditional noise rates and the performance assessment. Essentially, we will try to cover a combination here, a bunch of papers, one by Nagarajan Natarajan et al. And a follow-up a JMLR paper by the same, essentially same set of authors, and Gregory Partini et al. Under this setup. We'll come back to the class conditional noise in some way or another way down the line later, but we'll try to spend some time understanding this next level of complexity in the label noise setup. We are moving to the setup where, apart from the simple label noises, recall the class conditional setup essentially means that the +1 label will be flipped to -1 with what we denote by rho plus flipping probability. And when the label is -1, it will be flipped to the, so y tilde. Throughout our presentations, we'll stick to this convention in this community. Generally, the unscripted things are clean data or clean underlying law, and the tilde will usually refer to that there is a that is the sample or the variables coming from the corrupted labels. So when we say that y is equal to -1, it means the clean unknown label, of course, is -1. That y tilde is flipped from -1 to +1. Y tilde will mean it is a flipped label or the corrupted data point. So this probability in the class conditional setup will be rho minus, whereas the other one is actually rho plus. So obviously when rho plus is equal to rho minus, the CCN model reduces to the SLN model. So, or in other words, SLN model is the first level of, in some sense, generalization of the CCN model is the first level of generalization to SLN model. All right. So one more reasonable assumption. So in that sense, this is also a bit more reasonable and so-called practical model in some sense. Generalistic CCN is basically a more realistic model because it at least addresses to the fact that the flipping probabilities can be class dependent, unlike the SLN. So this bunch of papers actually, they also give performance guarantees. So what are these performance guarantees in general? So in some sense, these are the first bunch of papers who actually went beyond designing algorithms who are actually noise robust. They also gave accompanying performance guarantees. Usually the performance guarantees are actually high probability bounds on the risk of the designed classifier. So that will be usually a high probability bound, and the high probability bound will talk about a suitable performance, maybe the accuracy of this design classifier, vis-a-vis the theoretically good clean data type of thing, and how is it deviating. So that probability should be fairly high for low enough errors. That is what I mean by the high probability bounds. So I will illustrate it down the line, a specific example of this a couple of times down the line, but these are the performance guarantees. Generally we'll address it. Okay. Now, the way to go about is this, given a loss function L, one defines an alpha weighted version of it. So this alpha weighted version is actually that when the label is say +1, this is indicator function. I mean 1 y is equal to 1 will mean actually indicator function, which takes a value 1 when the label is 1, the clean data labels. Then if there is a loss there, that will be called, that amount will be 1 minus alpha. Alpha is actually a fraction between 0 and 1, positive fraction. For the other type of error, then y is equal to -1, then the loss will be alpha. So this is so given a loss function L, we wrote it compactly, the community writes it in compactly, the L actually can be written, and you expand the bracket simply and expand it and associate L here and associate the same L here, then you will understand actually why this is called weighted loss, alpha weighted loss. In particular, when alpha is equal to half, this is a good old 0-1 loss function actually. When alpha is equal to half, this is a good old 0-1 loss function. So given that what I mentioned a few minutes back about class imbalance and cost sensitive type of things, so this is the example of cost sensitive loss functions. So if you feel that one particular mistakes while the classifier on about one particular class are more important, one can use this. That is essentially the way, and alpha can be chosen suitably such that one of these two terms is very high, depending upon the type of mistakes you are interested in. Then if alpha, if the loss function L is also bounded, then they define what is called L tilde. T is the symbol for actually the it is a running symbol for f of x, the classifier, and y is the label. So throughout most of it, we will be working with actual margin label, margin based loss functions. But many a time actually will differentiate as the community keeps doing it. The first argument of a L or L tilde will usually the f of x, denoted for the simplicity by small t running variable, and why the second argument is of course the label. Then they cook up, given a loss function L, they cook up a particular loss function in this way. So as you can see, this is a ratio of two terms. This will be 1 minus this rho minus into L and rho y into L at minus 1 by this 1 minus rho plus and rho minus. The thing about this particular L tilde is actually its mean or its averaging with respect to the cal d tilde, the corrupted underlying law is actually original L. This is what they call L tilde is called unbiased loss estimator of the L. For this reason, this is called unbiased loss estimator. Nagaraj and Natarajan et al. They mentioned this. This is a terminology. It turns out actually using this a version of this unbiased loss estimator. One can argue that using a version of L tilde, that is unbiased loss estimator, will be noise robust to the class conditional noise models. Okay, that we'll see in the next slide. All right. So in particular, if you instead of working with L tilde, one works with the alpha weighted one as well. The property will hold because alpha tilde L alpha is also a bounded loss function, and one can work with this and one can argue this. So what is L alpha here? The L alpha is the alpha weighted version of the given loss function cal L. L. So now consider the following ERM scheme, which is essentially ERM scheme. Okay. Well, generally one will write in an ERM setup 1 by m, but we are doing an argmin or argmax, so the scaling of 1 by m doesn't matter. So one can, if you want, you just visualize it 1 by n. And this is basically the sample average. If you write a 1 by m, this will be the sample average, which is a classical thing in the in the ERM setup. So what are you trying to do? What is one trying to do here? One is doing a sample average in ERM on the noisy data. The given data is a noisy data, y tilde. And what is the loss function that is being used in this ERM setup? That is the unbiased version of the weighted loss function. So you have an L and you do two transformations on it. First, you look at a alpha weighted version of it, and then look at the unbiased version of it. That is alpha L tilde alpha. That is a summary of that two transformations on this loss function, and do an ERmin. That's why you are looking at an argmin over here. Let us call the classifier that you get out of this exercise as f cap. So then for a given classifier, before operating on this argmin, imagine the intuition. We'll try to in this tutorial we'll try to give some intuition as to why some things are working. For example, here the intuition is actually is that because this unbiased thing, essentially this ERM converges to the true risk of the given f, as if it is working with the clean data because of the unbiasedness. That's where the unbiasedness of the loss estimator that was introduced in the previous thing is actually important. So that is a whole key for this intuitively. One needs to work it out in detail, but one can work it out. So given a classifier f, the sample the above converges to the true risk, even if the data that is used in this computation, as we are seeing here, is actually from the corrupted thing, as long as it is the CCN setup. So this is what they mean by the unbiased loss estimator method for designing a classifier using the noisy data when the noisy data is in the CCN setup. So the other comment I want to just make it here is actually is that okay, so let us get going. So let's recall that in the meanwhile, that while defining the L tilde, the transformations, the noise rates are used actually, because in the, if you recall, actually it has, for example, all over both in numerator and denominator, the noise rates are there. For example, in the denominator, there is a quantity called 1 minus rho plus minus rho minus. So one needs to know the noise rates, but noise rates are usually unknown. It is desirable to say that noise rates are unknown. So the last step in their ERM scheme is actually to do a cross validation over this noise rates grid. So they assume a set of values for the noise rates between 0 and half, and the noise rates for the rho plus, and similarly for the rho minus also. And they do a cross validation of the above ERM scheme among these things and find the best, find a classifier which actually fits, which yields the good test rates on the cross validation schemes. So that's how they actually propose their method. So now I think I need to speed up a bit. So their next performance measure that I mentioned, one other thing about this particular paper is actually is that they also talk about, as I mentioned in the earlier cases, performance guarantees. So in some sense, as far as our understanding goes, this is the first paper to talk about a performance guarantee. So this high probability bound that I was mentioning to you earlier. So the true risk of the design classifier will be upper bounded by some quantity, a computable quantity. That probability, basically the probability that the true risk, true and unknown risk of the design classifier is not more than some quantity, that will be with high probability 1 minus delta. That is a way one can understand these high probability bounds. I hope I'm clear. So the left hand side is unknown quantity RD L alpha, because F cap D is not known. That's the main reason that's why I call this as a true risk of this F cap. True or L alpha risk in the true setup. This will be upper bounded by computable quantities. It turns out actually all these quantities are actually computable, more or less. For example, if you are talking about a delta, M is a sample size, this is a delta that you want to plug in here. So 1 by delta is computable. The RC is the Rademacher complexity of the classifier class that you are looking at it. In principle, it can be computed. And L rho is the Lipschitz constant of the loss functions that one is using it. So essentially most of these quantities actually can be right hand side. This is a base risk in some sense in this class. This is also theoretically we can compute it. So that is in some sense these three terms essentially are computable. So one is upper bounding the unknown quantity here by 3 computable terms with high probability. So that is the performance assessment they were able to give for their algorithm. There are variants to this result in that particular paper. Some of them we won't go into this detail in this particular tutorial for want of time and things like that. Essentially, they also talk about an online version of this, and they also talk about a variant of another algorithm which actually exploits the convexity properties of the surrogates. So for the time being, we'll not go into the details. Okay. All right. So the next particular paper okay. So they are, I want to mention one more thing in this particular paper. They also address some other performance measures other than the accuracy. For example, look at the confusion matrix, and they define the confusion matrix will have these 4 entries: true positives, false negatives, and essentially the true negatives. Those will be the entries in the confusion matrix. So they look at what they call utility of a function f, which is actually a linear combination, a linear combination of these confusion matrix entries essentially. So AIJs are actually given for them. And so, for example, the advantage of this type of approach, utility actually is that this performance measure called arithmetic mean will be included because for this choice of A11, which is 1 by 2 into 1 minus pi, remember that the pi is the probability that label is 1. That is a probability with which actually the entire, in the unknown D, what is the mass of the positive labeled classes or label 1 classes. Essentially, that is the intuition one can give. But the choice of A11 1 by 2 into 1 minus pi and A0 1 by 2 pi, here is the pi. So this reduces the arithmetic mean. So then the observation would be the base classifier is a suitable threshold of the in-class classifier for the AM. In general, for the 0-1 loss function, the base classifier has to be thresholded at half in the binary setup. If the performance measure is arithmetic mean, if the eta is thresholded at pi, that will be the base classifier by arithmetic mean. So they also mentioned for this arithmetic mean a high probability bound on the regret in the spirit of whatever we mentioned in the previous slide. So summary of this type of paper is actually is that they address performance measures other than accuracy, which is fundamentally more important. Like in particular arithmetic mean or a linear combination of these confusion matrix entries. And they also offer a performance guarantees for this type of thing and identify that a lot of loss functions are actually satisfy their setup, and hence one can design noise robust algorithms when as long as the noise is actually CCM. The final step, as I mentioned earlier, is actually they do issue indirectly the noise rates in the sense that they cross validate their entire algorithm over the noise rates. All right. Okay. So we'll move on to some other paper which actually appeared almost in a similar time by Gregory Patrini et al. So given this uses the ideas of what is called sufficient statistics and factorization theorem essentially. The overview is here. Given a data, in particular the S is the sample, they define what the quantity called, which is actually a vector mu S, the S denoting for the sample, which is actually the sample mean of y into the x vector, the feature vector. Recall that x is our feature vectors. Fine. So that's why they call it as an empirical mean operator of a learning sample is defined like that. Then they have a notion of what is called a linear odd class of functions. So given a loss function L, look at it L of x and look at its sort of mirror image in some sense in the margin setup L of minus x. Look at the difference and divide by 2 essentially. So you will sort of realize or get an intuition that actually this operation is actually picking up in some sense the odd component, the so-called odd component of the loss function essentially. That is the reason why I believe that they call it as linear odd L. The linear they call it because if this operation, this L of x minus L of minus x by 2 is actually is equal to is equal to A of x for some suitable A, then they call such loss functions as A linear odd L loss functions. So the first observation or one result they have is actually the mean operator that we defined here is actually what they call sufficient statistics for the linear classifiers for all LOL loss functions. If one has a LOL loss function and one is sticking to the linear classifiers, then the mu that is this sample operator is actually sufficient statistics. So the idea of the sufficient statistics in general is something like this here. Usually one has a parameter and one has an estimator for that, and some estimator is a sufficient statistic for that parameter, because any further transformation of the estimator will not give you better estimate, quote unquote better estimator basically. That is the intuition behind sufficiency. In that sense, it is a sufficiency idea. These are beautiful ideas due to sufficiency. Debabrata Das and they had fundamental results long back. Essentially, if we have a sufficient statistic, if an estimator is a sufficient statistic for an unknown parameter, then any transformation of that estimator will not yield a better estimator essentially. That's why in that sense this idea is called sufficiency. So what these people have argued in the label noise setup is that this mu operator, when you are using a LOL loss functions, is actually a sufficient statistic. That means that one need not actually do more operations on this mu operator to get better results essentially intuitively. Fine. So okay, so given a loss function L and one can do this, then the first observation. The next observation is that based on this, they will identify and decompose the error of the true risk of the classifier to be decomposed into nice terms in the next slide, and that will mean that what they call factorization theorem. If the classifier is linear, then using a loss function L, which is ALOL, that risk of that classifier under the sample when the L risk of the classifier essentially, the left hand side is L risk of the classifier on that sample can be decomposed into two terms. The first term is half of the one risk where essentially you have a sample S, they create an artificial sample by doubling the sample size in the following sense. For every feature data point, they create one more avatar of that of the feature with the label flipped again. That's why the notation is 2x. You have a sample M, they create a 2M samples by repeating all the features excess. And what about the labels? Labels will be actually flipped and again repeated. So essentially the 2x is double sampled with feature x repeated, and hence it's actually label free. The data, now the 2m sample, 2m size sample is actually label free in some sense, because each label will be repeated in some sense. I mean, rather the feature the label is immaterial, because for the any given label for the small x feature, we'll have another data point with the same small x but the corresponding other label. Fine. So their observation is actually is that they also yield, they also provide a high probability performance bound in the spirit of whatever we mentioned in the Nagaraj and Natarajan et al. Paper of a different nature involving this type of loss functions. And this bound will have a term that doesn't blow up actually the way that the Nagaraj and Natarajan et al. Paper has this, because in the Nagaraj and Natarajan et al. Paper, the term and the performance bound has a term called 1 by 1 minus rho plus minus rho minus x. So if the noise rates rho plus and rho minus are actually both are very close to 0.5, then the denominator is actually sort of blows up. So the bounds that are given actually will turn out to be weak. So whereas this particular approach yielded, this approach of ALOL functions will yield a performance bound that has actually a multiplier 0.1 irrespective of the noise rates. So, okay, this particular paper has some other strands also, weakly supervised pick it up. Some of those points will come to it a bit later if we have time. But for the time being, this is a summary of that particular paper, results from this particular paper as specialized to class conditional noise rates. All right. Okay, so yeah, so maybe now onwards, I think Sanjay will take over for some amount of time. Down the line, actually, in the entire tutorial, we will keep on flipping it topic wise, and maybe this is one more switchover we'll make in these presentations. Okay, yeah, we can go ahead, Sanjay.
Okay, so till now we have been looking at majorly the loss functions and loss functions that have been classically used in the machine learning literature, but recently Liu and Gyo, they proposed a class of loss functions called pure loss functions. This loss function comes from is inspired from a different area called pure prediction framework, where basically there are k agents and there is a ground truth which is not known or is not verifiable, and the k agents that are available, they also will report the will report their value of ground truth with some noise depending upon how you are going to reward them. So basically it's the problem in peer prediction is how you can elicit information from self-interested agents without verification. And this reward function or the compensation is done by the score function S, and generally S is designed in such a way that S is designed in such a way that all the agents are truthful and Bayesian-Nash equilibrium is reached. Bayesian-Nash equilibrium. So by Bayesian-Nash equilibrium here we mean that if I am going to say, like, given the other person is going to tell the truth, my best response or my best option would also be to tell the truth. So this is the framework which they have used here. So S is the reward function, YA is the report of agent A, YB is also the report of YB is a report of or the noisy observation of ground truth by agent B. So what the authors here did was they mapped between the peer prediction framework and the noisy learning problem. So here the YA or the reward to the agent to whom the reward will be given would be mapped, or the report of this reward would be mapped to the classifier's prediction fx, and YB, the reference report, would be the noisy label. So when you maximize this reward, it turns out to be minimizing this loss function called pure loss. So so this S is generally defined as the difference between two quantities. One quantity is the uh, one quantity is one quantity is the reward to that particular agent A, and then sample one to that agent A, and the other quantity is also is a function of the reward to that agent A and B both. So one particular concept that is important here is correlation agreement. So this correlation agreement builds a delta matrix that captures the stochastic correlation between YA and YB. This matrix is a 2 cross 2 matrix, and then which is further used to compute a matrix M, and then finally this reward function S is computed. So when rho plus, so under the simple assumption that if rho plus rho minus is less than 1, sign of the delta matrix in case of label noise turns out to be an identity matrix. So the whole algorithm, which how it works is you find the pair samples, that is you randomly draw two distinct noisy samples, that is M1 and M2 for a given sample M, and the loss, the pair loss would be computed as the difference between the loss uh, loss of the prediction made on XM and with the true value of y tilde M, and the loss of the the sample M1 when it is compared with the original label of M2. So, and now if you see, if this L here is indicator function and the class prior pi is 0.5, that is the data is balanced, then they showed that the minimizer of this corrupted true pair loss risk, that is a minimizer of the risk of with respect to this loss function, is equal to the clean base classifier. So one thing to note here is that this is inherently class conditional noise robust. That is, there is no the noise rates rho plus and rho minus are not going to appear in the optimization problem. So you don't need any knowledge about it, or you don't have to cross validate over them. The other thing here to note is that so they showed it for indicator function, that which if you substitute it here, it turns out to be ultimately LPR turns out to be a version of a modification of 0-1 loss, which was earlier shown to be noise robust. But that case, it was shown to be noise robust to symmetric, only the uniform noise. Here they have a more general result or a stronger result where they show that it is inherently robust to class conditional noise also. So this was a pair loss function, and now there is one more interesting literature in this area, or for the empirical risk minimization setup, is by Tongyang Liu and Dacheng Tao. So what they have done is they basically reweigh the data points. That is one approach, and propose a solution for estimating the noise rate. So but that is the solution or the empirical results does work, but it is difficult to estimate the noise rate. That noise rate will depend upon the in-class probability, which is hard because of density estimation. So next we move on to some multi-class noise robust loss function. Ghosh and the group, they provided a sufficient condition for robustness of multi-class losses under uniform or symmetric noise. So this sufficient condition is an extension of what we saw for the binary class. So in binary class, you had so you had two labels. So it was just L of L1 plus L minus 1 equal to some K constant. Here, since there are many classes, the sum is over K classes, and again they want it to be C. So if your loss function satisfies this condition, then it will have the property of noise robustness against uniform or symmetric noise. So they tried various loss functions, in particular categorical cross entropy, mean squared error, and mean absolute error, and showed that this particular mean absolute error is noise robust, and that's because if you sum it over all classes, it turns out to be 2 minus 2k, which is a constant. And for these two losses, the sufficient condition is not satisfied, but for categorical cross entropy, sorry, for MSC, this is bounded, so it enjoys more robustness properties in comparison to categorical cross entropy. Now we see that mean absolute error is robust, but the problem with it is that it is difficult to optimize it, as its gradients saturate very quickly. So how can we get away with it? There have been many people who have come up with very interesting loss functions, where they try to utilize or exploit the properties of categorical cross entropy, or CCE, for designing loss functions. So we'll see some of them. Yeah, so like I said earlier, that CC is not robust, but a lot of research has been going on, which where they modify it or inspired by it make design loss functions that can be either theoretically or empirically proven to be noise robust. So the first one of them is robust log loss. So the robust log loss is again based on the idea that mean absolute error enjoys robustness, theoretical robustness, but its gradient saturates. This CCE doesn't have the robustness property, but its gradients are flexible, and they go a long way. So so based on this, I defined a loss function called robust log loss, which is basically the log of this term alpha plus 1 by alpha, and then the sum over a noisy version or a smooth version of the probability estimates for other classes. So here P hat is the prediction of the neural network. These are probabilities, and EJ is the true label. So it will be a vector or one hot encoded vector, one hot encoded label vector. This was one case. The other more popular one is the generalized cross entropy, that is GCE. So it's again inspired from the fact that CCE puts more emphasis on training difficult samples. So in case of noise, in case of clean data, this is a good thing, because it starts from easy and then goes on to difficult ones. But in case of label noise, it could lead to overfitting, because your test sample is going to be ultimately clean and you won't be able to generalize well there. So they used a box-Fox transformation and defined this loss function called LQ, again on P hat, predicted probability, and EJ. And this particular loss function can be specialized to cross entropy or MAE, depending upon whether Q takes value 0 or Q takes value 1. So this is generalized cross entropy. Third is a symmetric cross entropy loss function. So here the authors basically say that CC, as known, it overfits on easy or easy classes, but underfits, sorry for the typo there, it has to be classes there, easy classes, but underfits on some difficult classes. So inspired by the symmetric nature of KL, they designed a loss function which basically adds up cross entropy plus a reverse version of it. What do you mean by by reverse? We mean that the probability and the true labels in the cross entropy, like here, are flipped. That is, this part is the coefficient of alpha is the cross entropy, original cross entropy loss, and the coefficient of Beta is the reverse cross entropy loss. The beta provides flexibility in robustness because reverse cross entropy has been shown to be robust to robust to uniform noise, especially, and alpha is the parameter which takes care of overfitting part in cross entropy. An example which the author showed is can be seen here. So this is for MNIST class. This is a two-dimensional representation of the last second layer. They used last second layer's output. And as you can see, this is the cross entropy loss and each how mixed, like combined it is. And the symmetric loss, the output or the representation via symmetric loss is more clearer and the labels or the classes are easily identifiable or distinguishable here. So this was symmetric cross entropy. Next, we have another loss function. This is not really inspired by cross entropy, but this particular loss function is it's important because it doesn't even depend upon noise rate. That is one thing. It further also doesn't depend upon the noise type. So till now, the loss functions which we have been seeing, they were majorly noise robust to uniform noise. But this particular loss function, LDMI, that is a information theoretic loss function, it doesn't even depend upon the type of noise you give to it. So it relies on the determinant-based mutual information, which is a generalized form of mutual information. And like I said earlier, it's robust to any type of noise and any noise level. So the structure here, the structure of LDMI loss can be seen here. You have corrupted data points, you train a classifier, and then get the outputs of that classifier. Each row here would be the probability vector for, sorry, each column here would be the probability vector of an example. And then you have original labels, that is the corrupted labels. So each again each row here would be the true label vector, and when you take the joint distribution over them, you get the loss function here, which is LDMI. So in other words, it can be written as, if U is the matrix product of OL, then LDMI is defined as a minus log determinant of U here. So this was multi-class loss for multi-class loss, that is independent of the noise rate, the noise type also. Now there are many such loss functions, like the most recent one is a class called active passive losses. So what they do there is they start with a suggestion of making the losses normalizing the losses, and show that the normalization technique can make any loss function noise robust, but it's not sufficient that the loss is noise robust. Its empirical performance could be bad. So in that case, they propose active passive loss functions, where active losses, if you have for one particular example, the active loss basically is the label and the prediction matches. That's the active loss. And similarly, passive loss is also defined, and then they take a combination of these two. Another physics inspired loss function is bitempered logistic loss. They have a temperature parameter over there, and they showed it to be robust again to only symmetric label noise in the multi-class setup. So continuing with the extensions or the loss functions which stem out from categorical cross entropy, we have trimmed categorical cross entropy. So here what they do is you compute the cross entropy for each data point, and then you order the loss of all the data points in your training set. And after ordering, you order it in ascending order, and then you decide a threshold edge, decide a threshold edge that where you want to stop, and that threshold edge will decide which part or what type of not what type, what level of noise the loss function is going to be robust to. So for high values of f, the loss function or the algorithm based on this loss function would be robust to high level of noise. And if you, that's what the empirical experiment showed. And high level of edge would lead to, again, algorithm that is only robust for low noise rates. Another one is Taylor CCE. Taylor CCE basically uses a Taylor expansion of cross entropy loss, and the one can control the terms that are included in the loss function. This is the most recent one. I think it appeared in ICHCAI this year. So these are all the loss function based approach, as in these here the idea is majorly to identify a loss function or design a loss function that is inherent to label noise, inherently robust to label noise in the multi-class case, or to be used in neural network. But the other approach could be to correct the loss function that has been majorly done by, started by Patrini and group in 2017. So the multi-class classification setup here is again the C classes or K classes as we had used earlier, and the network's prediction is P hat. So if T is the noise transition matrix, that is like we had rho and rho plus earlier, T is a generalized version of that rho plus rho minus in the multi-class case. And if this is known and rho stochastic, then they propose two approaches. One is a backward correction approach, which basically requires the inverse of this T matrix, and the loss correction was found to be unbiased. And like earlier, we see that if you can design a loss function which is unbiased, then your risks on the risks on D and risk on D tilde are same, and hence the minimizers would be same. So now the other thing which they did was which they proposed was forward correction procedure, which is which exploits or which relies on proper composite losses. So proper composite losses are the ones they have a property of they have a property where the link function they have can be can take the particular shape of the eta or the in-class probability which they get. So here, as you can see, if L phi, L psi, that is a proper composite loss, then its minimizer assumes the particular shape of link functions applied to py given x. This is the eta which I'm talking about. Now they showed that this out of these two, forward correction procedure is better, and forward correction procedure is better, and they the statement or the claim which they say, or the insight which they provide based on this, is that it is not better because of the statistical properties. It is just better because it doesn't have to go through the problems of inverting a matrix or numerical issues that could arise in the backward correction procedure. This was the case when if you think that if you assume that T or the noise transition matrix is known, but generally that's not the case. So you have to estimate T. One one technique which was earlier also suggested in case of multi-class to estimate noise is as follows. Here what they so if you assume that there is in your data set you have an example which has there are perfect examples. So by perfect examples I mean that their in-class probability would be 1. So eta x equal to 1 if the label is positive, and eta x equal to 0 if the label is negative. So if those examples exist in the data sets, then you can actually estimate the noise rate. So but in reality you don't have the whole data set, so you can't see whether that happens or not. So how you go about it is you first find a x such that for each class you find a x which maxima with that has the maximum predicted probability, and then with this x tilde or use this x bars in class probability to as an estimate of the t matrix, that is t hat ij would be the probability or the class probability corresponding to this x bar j, or a proxy for a perfect example which we have. Now recently Lucasis and group, they showed that this loss correction approach loss correction approach either by Patrini and group or by Natarajan and group earlier, that is that works well because of the label smoothing, and further label smooth or not works well, but there is a connection between label smoothing and these loss correction approaches. And label smoothing is traditionally or till now has been known to improve the performance of neural networks. So if you attribute and they showed that this property of label smoothing of denoising can be attributed to the L2 regularization property, or it can be related to L2 regularization or L2 kind of regularization. So one more thing which I want to say here is that label smoothing is just smoothing or mixing the one hot encoded labels with uniform noise. So people might say that, oh, you already have noise in your data set and now you are inducing more uniform noise to your labels, but that's what Lucasis and group showed, that even though it might seem counterintuitive, but this particular approach of label smoothing does help, and it is indeed comparable or competitive to the loss correction approach by Patrini and group. So another modification or network-based approach for dealing with noisy labels is co-teaching. Here, this is a different line of work, in the sense that instead of designing a loss function or making a loss function robust or making an algorithm robust, they try to identify or they basically try to identify loss functions, not loss functions, sorry. They try to identify the data points which could be possibly noisy. So how they do is this: they exploit the property of TNNs, that neural networks generally learn easy instances first and then move on to difficult instances. So this property was earlier also exploited by MentorNet and decoupling, but here in the co-teaching setup, what they have shown is that the information across these two these two networks in decoupling is not passed enough, and it's a so even when a certain number of iterations have passed, the number of noisy labels which you are dropping, if it is constant, then your network actually is could be overfitting. So what they suggested is they proposed the propose this kind of architecture where the updates would be passed across the networks, and the updates would be passed only for small loss based examples. And why small loss based examples? Because the correct labels would tend to have small losses. And the other interesting thing which they do here is that as they keep the batch size high initially and then start decreasing it after a certain point in learning, because if they keep the batch size constant, like I said earlier, they might lose out on good examples too. So also the networks will have different learning abilities, so they can filter different types of errors introduced by noisy labels, and that can further be improved by the peer networks updates. Now till now we saw that we only have noisy label data, but Hendricks and group in 2018 questioned that and said that why can't, like, if there is so humongous data and we have so much of available data and we know that it could be possibly corrupted, why can't we just get some clean data by paying someone and then use that data as a reference to learn from the noisy data? So that's what they proposed here in this paper, and the main idea is they leverage the fact that a small set of clean label is often procurable, and they call it gold standard. The clean set is approximately either 10% or 15% of the total training set. So here also they have to estimate the corruption matrix, which was called P earlier. Now in the paper they call it C. So how do they do it? They learn a classifier on corrupted data and then use those averaged probability predictions to compute to compute the corruption matrix. Once the corruption matrix has been estimated, they move on to any loss correction approach and use that estimated matrix over there to finally make predictions. So one major strength which they claim in their work is about the estimation of noise matrix. They claim that the technique which they have proposed is good for noise matrix estimation, which they demonstrated here also in a figure. So if true noise matrix is like this on the top left, then the proposed method, that is GLC, gold loss correction, is almost getting all of them correctly. And the forward here is a forward procedure by Patrini and group. It is okay, but not that great. And then if there is another method called confusion matrix method, if you use that one, then you are like really in trouble while estimating the noise rate. But even after all this, they do caution that estimating noise rates is here again estimating the probabilities and density estimation, which is a generally difficult problem to study. Now after this, we tried using this idea last year, that there is some clean data available, and but we said that okay, 10% is still too much. Can we do better? Can we do better by reducing that 10% amount clean data or clean label data to say maybe 1%? And we got some result in that. So we use it. The technique which we use there is of using GANs, generative adversarial network. So I'll just briefly describe the GAN. Most of you might be knowing it. It just in a GAN, there are two networks which are competing against each other. The generator is fed with random noise, and the discriminator is fed with real images, and the job of the generator is to learn the distribution of these real images. This generative adversarial networks, when they were proposed, they were majorly for generative purposes and not for discriminative purposes. So we have, like, what we have proposed is a little different by using them in a discriminative setup. So okay, so here is the setup which we propose for learning with label noise using GANs. So the main idea here is that there are two networks, again, discriminator and generator, and instead of just features or the random noise, Gaussian noise, which was fed in the original GAN, we are going to feed the whole noisy data, that is the example or the data point the feature and label pair, noisy label pair, to this particular generator, and we are going to feed the clean data to the discriminator. And the idea is that GAN should be able to learn the joint distribution correctly and output the joint distribution also. So here the clean data is fed to the discriminator, the noisy data is fed to the generator, and when we are finally and the generator, after certain point in training, the generator will generator is expected to start outputting clean label data. So clean label data, the two major issues here were that how do you make sure, because if you have X here, this is generally a real vector, and for images this is some very high dimensional number, and Y is just either 0, 1, or at best classes or still categorical. So when you are just appending these two and feeding it to these very complex networks, how do you make sure that your label is still represented? So one thing which we tried was that we tried to scale the value of the labels and repeated them, say 5 or 10 times, so that the representation, the networks are still able to learn from it. And this was the first stage where the whole GAN will generate correctly labeled data, and now this correctly labeled generated data set would be fed to any classification model, and the output would be used for evaluating the performance. So this is the performance of the WGAN-Y which we had, and this is for the imbalanced binary version of the MNIST, but it worked well. It worked well for the general setup or the balance setup also. Here we are just showing for the imbalance setup, because this is an additional advantage in the sense that we did not do anything to account for imbalance or to account for imbalance in the data, but still the network or the whole setup is able to do well, especially at high noise rates. So like I said earlier, GLC, which is known to be noise robust, is at high noise rates, that is close to 0.5, that is 0.7 or 0.51. The GLC goes really bad, but the WGAN-Y still is able to maintain good AM performance. Yeah, this is AM because of the imbalanced data set, and the other thing is that it is stable. It is stable as in the distribution has been, so if it is stable, it means that the distribution has been actually cleaned. So the distribution has been actually cleaned, and you have the original you have the data as if from the original distribution. So now this was majorly majorly the deep learning literature and the label noise intersection. There are others like recent ones that have come up, not like loss function approaches, but more like additional, more like from the point of optimization, or more like from the point of optimization or basic fundamentals of how neural network works, exploiting them and trying to identify where can be tweaked to make the network label noise robust. So one such study was by Chen and group. They related the noise rates, that is the rho plus and rho minus, to the test set accuracy. So they showed that the test set accuracy is equal to the ratio of noise rate, especially in binary classification, and using that they proposed an algorithm that is label noise robust. And the most recent one is stochastic integrated gradient gradient ascent, stochastic integrated gradient underweighing ascent. Here what the major idea after in these four or the major concept this literature work with is that the working of neural networks, that is they start learning on easy examples earlier, and then after a point they start memorizing. So they'll memorize little bit, and then after a point the memorization could be on the bad examples. So, and the bad examples here would be the outliers or noisy examples. So the SIGWA algorithm avoids this undesired memorization in over-parameterized networks by reducing the learning rate for ascent when they are doing gradient ascent on the bad data, which is basically outliers or corrupted labels. Another work is by Yang and group, which is based on search strategies. That is again, the idea again here is that initially the networks will learn the good examples and then later on the difficult examples. So now they proposed or they formulated a bi-level optimization problem, which is basically used to or decide how many examples to discard that are supposedly noisy at every iteration. And the bi-level optimization problem is shown to be working really well in comparison to the existing state of art. Another work here is based on information theory. So here what the idea they exploited is that the Shannon mutual information between weights and the vectors of training label quantifies the memorized information. So if this information is, you have a quantification of this how much is the memorized information at every iteration, you can effectively stop or decide again how many examples I want to discard at every iteration. The final one here is early stopping based. So the authors Lee and group they show that the first order methods, they will work if you use first order methods with early stopping for training over parameterized neural network, they actually make those neural networks robust to label noise. And there are many more. We'll be happy to share the slides later on with all the references. And yeah, so till now it was mainly either symmetric label noise or class conditional label noise. But there is a third category, or a more general one, that is instant dependent noise, which sir will be discussing about.
Okay, so this is another model where the name is actually instance dependent in the sense that the unknown noise rate, of course, actually depends upon the feature X. So it goes back to again some work by Aritra Ghosh and Patapat Sastry and Naresh Manwani, that type of that group of people. Okay, so recall that in the SLN setup, symmetric label noise setup, a sufficient condition was shown to be sufficient condition was derived or identified, that of L1 of f of x plus L minus 1 of f of x is equal to k for some k, then that loss function L, which has this L1 and L minus 1 as components, so to speak, is noise robust. This L was decomposed in that setup. And many loss functions were actually, primarily the 0-1 loss function was known to be SLN robust because of that reason. Now, if the noise, that is an SLN setup, that the rho x becomes effectively rho, a constant rho, no matter what the x is. If the model is such that the noise is actually instance dependent, rho x, then supposing we have another condition that the true risk is actually 0, then such a loss function L, which has this conservation property, they call it as conservation property type, is actually noise robust for this noise model rho x. So I guess, I hope I'm clear. So basically there are two conditions for a loss function L to be noise robust when the noise is actually instance dependent. The one is this L1, L sub 1 plus L sub 1 should, L sub minus 1 should be constant, and the true risk should be the 0. Okay, so yeah, in fact, if one works out the proof or something like that, actually one will observe that not only the, okay, what do you mean by noise robustness? The noise robustness is actually, say, the accuracy is same, no matter whether you are trained from the noisy data that is actually available or the hypothetically clean data. So in fact, what works out, if one works out the details, it will observe that actually not only the noise rate, the test set accuracy is same. In fact, the classifiers will be actually same. Even though you actually train on the noisy data, the algorithms that uses this loss function, which satisfies these two properties, yields a classifier which it would have yielded if it actually trained on the clean data. So no wonder actually the accuracies are same, because the classifiers are actually tallying. All right. So then, so essentially it means that if the true risk is actually R star is 0, then the 0-1 loss function is robust to non-uniform noise as well, because the first condition anyway is met by the 0-1, the good old 0-1 loss function, which is actually, yeah, it is not even continuous, forget about differentiability, but of course it is piecewise constant and all this stuff. If the true risk is 0 as well, then the 0-1 loss function is noise robust for the instance dependent setup as well. Now, again, continuing with the same thing called true risk is 0. In addition to the 0-1 loss function, these are the three loss functions actually which will satisfy essentially the first condition, and hence there are noise robust to instance dependent noises as well: the sigmoid, the ramp, and the probit. So here are these margin representations of these loss functions. So what I wrote is actually the margin representations. The sigmoid, if you recall, is 1 by 1 plus exponent b. Some beta is a tuning parameter, beta fxy. This fxy is a margin. Okay, we can write it as fxy or f of x into y or yfx. So this is the margin. So all these are margin representations. The ramp loss is actually a combination of two linears. That's why it's called ramp, I suppose. And the probit, the psi, okay, we didn't write it in detail here. The psi is the CDF of the 0-1 standard normal, mean 0 and uniform unit variance. So these, one can argue that these three loss functions are also satisfy the first condition. And if we make the extra assumption that the clean risk is 0, then these four loss functions actually will be noise robust to the model where the noise depends upon the data point, a feature point X. Yeah, okay. So the catch is that in the last three is for sufficiently large respect to beta. So each of these loss functions may have their own threshold. So beta sigmoid or beta ramp and beta probit. For them, the loss functions will be actually are shown to be theoretically shown by Aritra Ghosh et al. Paper that this is noise robust for this thing. So it might, on the face of it, actually this condition that the true risk is zero is actually on the face of it is very conservative or very demanding. But if you think for a moment, it will the following are the comments made by those others. Actually, in fact, if one thinks for a moment, the clean D is actually a mathematical construct. That is actually a hypothetical thing. What is observable to us actually is the sample comes from cal D tilde, the noisy samples. So one is actually doing a backward reverse engineering type. Actually, we are starting from the cal D tilde, assuming some noise model and then associated a loss function, and we are sort of reaching the cal D, the clean joint law of the features and the labels. So this reverse engineering has essentially the end of this reverse engineering. The cal D is actually a hypothetical construct. Because we don't in practice we can't assess or get labels from the clean distribution in practice or in theory. I mean in the spirit of label noise, we don't have access to the clean labels essentially, except the some points where we made points and only small percentage like 1%, 10% is available. But that is also very low percentage is what people have assumed that. So for the respect to beta, if the beta is very large, essentially they say that this is working out. Now the intuition why these loss functions for large beta are robust to this instant dependent noise is essentially because for large beta these loss functions in the margin representation, they approximate the sigmoid, the 0-1 loss function, and hence no wonder that actually in some sense intuitively these loss functions are also noise robust for this particular case. Okay, so that is one intuition. Now coming back to the assumption about this that the true risk is zero is not very demanding in fact, because it is an artifact. We can think about it. So given the cal D tilde and a loss model, one can sort of think about at least some situations where this condition will be actually met. That is one comment. The second comment is that even if one is making the assumption that true risk is zero, recall that we are not learning from this clean data. We are actually learning from the noisy data. And okay, one way to rephrase this true risk is zero is essentially says that the data is actually linearly separable. That is one way to. In fact, the base classifier or the classifier which actually hits the true risk is actually a linear line in the simplest cases. In the simplest cases, the linear separable case noise data, if it is on the clean side, actually meets this condition. So since we are trying to learn or design a classifier from the noisy data, and the noisy data will in general will not be linearly separable. So using in this setup, in spite of this, what I'm trying to say is that in spite of this assumption, the label noise problem is actually not a very simple problem, because you are not learning from a linearly separable data set or a clean data setup, or separable or with a zero risk. So that is why this is there is a merit in arguing that actually this assumption, even though on the face of it looks very demanding, because it is an hypothetical construct, and if one makes some reasonable assumptions, one can actually do that. So that is one comment. The second comment, in the light of that comment, why these three loss functions are actually working in the sense that they are immune to or noise robust to instant dependent noise, is because for large respect to betas, they approximate the 0-1 loss function, which anyway is actually under this condition is of course noise robust also. So that is the summary. Okay, we can go back to the, we can go to the next thing. Yeah, essentially this is what I said. They're sufficiently steep. These loss functions are actually, if you just plot it, we'll observe that it is sufficiently steep near the origin, such that they approximate the 0, 1, the step function type, I mean, which has a discontinuity, the 0, 1 loss function. Okay, so there is one more this is a summary of whatever I mentioned. This assumption is actually not very restrictive by these people. In fact, what will happen is that one of those particular, okay, there is a small typo here. We should have been writing L01 here. If this is not 0, they construct a counter example where the L01 is actually not even is not noise robust among the linear classifiers. This particular paper by Naresh Monaman and Padapar Sastry has a counter example where they try to learn classifiers from the linear class where the clean risk is not 0, and that this loss function L01 is actually not noise robust. So in the light of this particular counter example, essentially what one can say is actually that this assumption that the clean risk is actually 0 is almost becoming something like a necessary condition as well. It is a sufficient condition, but it becomes some part of it is actually a necessary condition as well. Okay, so we can go to the next slide, Sandhya. Yeah. Okay, so here is one more sort of ongoing work with one of my other PhD student, Prashant Trivedi. So this comes where this assumption that the clean risk is actually seems to be arising a bit naturally here. The context is actually is that there are these ideas called a bunch of players trying to work with a cooperative game. The cooperative games are actually classical models, are very well-known models for what they call cost sharing. Suppose one set of people come together to do a massive work and they want to share the cost. Building a massive flyover, then there is a civil contractor, there are electrical contractors, and then some other contractors are there. They form together like a team and they can execute the entire job. And then the interesting question at the end of that successfully executing the project is how to share the costs. So the cooperative games, because they cooperated to form a task called some particular designated task, these are called cooperative games. And then in these cooperative games, the question is actually is the grand coalition formed or not? What is formed or not is decided by each player having what are called preferences and the coalitions they are going to form. So each player will have a preference whether which coalition they want to join, and based on those known preferences, one can predict whether the grand coalition is forming or not. One can predict it. So that is a standard theme in this cooperative game theory. The central question in cooperative game theory is actually is that under what conditions the grand coalition forms. So that depends upon the preferences. So yeah, the prediction of the stable grand coalition, one can view it as a classification task or a problem, because it is a binary thing. Grand coalition is formed is one class. I mean, that's a prediction. Other prediction is the grand coalition is not formed. So it's a binary. So now assume that the preferences are actually noisy. Now the classical thing in the cooperative games actually preferences are true and they are non-noisy. Suppose the preferences are actually noisy because the players may have some incentive or some motivation to hide the true preferences, so they can become noisy. But so hence and this model, this will be an instance dependent noisy label model. The label is quote unquote, the label is actually whether they want to form the grand coalition or not. That's the label in for them. So, but given the true preferences, one can easily predict actually whether the stable coalition is forming or not. So this will be met, this condition will be met actually. So essentially, if one works out some more details, it will mean that under the learning and under the setup where the preferences are actually noisy, those loss functions for large enough data can be used to predict or actually design a classifier or predict whether the grand coalition is forming or not based on the noisy loss functions, noisy preferences. Okay, any of those three loss functions can be used apart from the 0, 1 loss functions. Okay, so this is another setup where we mentioned that this is another basically we'll be covering many noise models. There will be quite a few, as I mentioned in the very beginning. There are various ways of looking at these models, whether it is a multi-class or a binary class, whether the loss function is used or ERM setup is used or not, URM setup is not used. Bulk of the work is actually is that to tweak a known or come up with new loss functions which are noise robust theoretically. That is a trend. It will go on. There are more models like instance dependent that I just finished now, and under this predicting the core stability in a cooperative game seems to be doable, even though it is the preferences are instance and noisy instance things, and this condition is essentially naturally met in some sense. Okay, so yeah, okay, now again I think you can take over, Sandhya, and we can keep an eye on the time as almost for something like 1 hour 45 minutes, no, since we started, or even more than that. Okay, we can have a word with the chair, and we can say there is a break time now for, we'll take a break for 10 to 15 minutes, and we'll come back and then we'll continue with this tutorial.
Oh, okay, or we can take the questions if there are any questions
in
the meantime.
Yeah, that is doable. Yeah. That is even better actually. Yeah.
Yeah.
If there are oral or typed questions here, we can address them in the material that we have covered so far. Essentially, what we have done is actually is that we have laid out some way of looking at it in terms of models, as I mentioned in the few minutes back, either in terms of is it a binary class or a multi-class, or is it actually predominantly ERM based loss functions, which loss functions are actually noise robust, or can we devise some new loss functions based on sufficient conditions. So there, if you recall, actually we covered so far actually the basic model symmetric label noise. Then we went into some details about the class conditional label noise, and then for that area actually quite a bit of lot of work is going on, even in the setup of ERM essentially, but deploying the neural networks and establishing some kind of relationship between the parameters of the neural networks and the noise robustness. And we also covered in the last one a short time on this instance dependent thing, and discussing the seriousness of the seriousness of the assumption that the true risk is actually zero. The observation is that actually CALD is anyway artificial mathematical construct, so one can actually assume that the true risk is actually, the CALD is such that the true risk of the base risk actually is zero. That is a summary of their arguments. Okay, we can take up some questions definitely, given this background. Okay, there seems to be not many questions or whatever.
Yeah, hi, this is Tim, the moderator. I mean, if there are any questions, you could just take a brief break.
Yeah, okay.
But people should feel free to either speak up or put questions in the chat. Either way would be fine, I think.
Okay.
Yeah.
Yeah, we basically wanted this break to take up questions, but yeah, if there are no questions, maybe in like couple of minutes we can start again. think we can start again if there are no questions then. I hope everyone is back. Okay, so welcome back. Till now, we studied label noise mainly in classification problems and how it can affect the classifier's performance. But learning is more than just classification. Now we'll see what is the more part there and what areas it can come up in. So the first thing is cost sensitive in cost sensitive learning, where there are differential costing of misclassifications due to the nature of decision systems, like in medicine where safety critical decisions are to be made, or the data could be skewed, like the number of customers defaulting credit card is very low, which is good. And so some direct solution approaches for this problem is you balance out the training data if the problem is coming from imbalance, or by balancing out, I mean that either you upsample the minority class or downsample the majority class, and there are various algorithms available for doing that. The other approach is you use an alpha weighted classification loss. So by alpha weighted classification loss, here I mean a linear combination or a weighted version of the 0-1 loss, where alpha is the weight for negative classes misclassification and 1 minus alpha is the weight for positive classes misclassification. And this alpha could be either user given or it can be cross validated for. So now there has been a lot of work in cost sensitive learning, and these loss function, and there are loss functions, alpha weighted loss functions, which are shown to be classification calibrated, in the sense that if there is a surrogate loss function which will perform well, which is performing well at very large samples, then classification if it would be called classification calibrated if its performance, if its good performance can be converted to a good performance in 0-1 loss sense also. But now and that all those theoretical results and all those good results are available only when you know that the labels are correct and they are not corrupted. But what if the labels are noisy there? So one result or one line of work was done, or the initial one was done by Natarajan and group in 2018. They published it in JMLR. So they considered an alpha weighted version as like was defined earlier also, L alpha. And as I said earlier, that L alpha, which is generally consistent in the statistical sense, that as the number of samples increase, the risk should go to 0. The L alpha in the presence of noisy labels loses its consistency property. So what they did was they proposed two algorithms, unbiased estimators, and two approaches or algorithms, one based on unbiased estimator and the other based on alpha weighted surrogate losses. The one thing to note here is that they cross-validated over the imbalance parameter alpha, and they did not call this alpha as the cost weighing. They called it. They considered the setup where they called it imbalance parameter alpha, and cross-validated over the noise rates also. So they did not bypass the noise rate estimation and did not consider the case which would be very prevalent, where the weight alpha is coming from the domain and is not tuned. Also, as mentioned earlier, accuracy is not a good measure for imbalanced data set because it will be dominated by the majority class. So they use arithmetic mean there. All this was good but there are a couple of questions there. First is, what will happen if alpha is given? How do you incorporate it? Should you just use alpha in the algorithm given by the domain, or should you still cross validate over it? And what about the estimation of noise rate? Can we bypass it? So we did some work in this setup, where the first question which we asked was is risk. So like earlier, we know that 0-1 loss is uniform noise tolerant. So we asked whether whether a weighted version of 0-1 loss is also uniform noise tolerant. The answer was no. We had a couple of counter examples for that. So if not 0-1 loss, can we find the surrogate losses which are noise robust? Surrogate losses good for cost sensitive learning, which are noise robust. There is one answer here, which is basically alpha weighted uneven margin loss functions defined by Clinton Scott in 2012. Before saying that whether it is noise tolerant or not, there is a new notion which comes up with the alpha weighted uneven margin loss functions, that is alpha gamma rho robustness of risk minimization. So the alpha gamma rho robustness basically says that if you have a loss function alpha weighted gamma uneven margin loss, then it will be robust to uniform noise if the cost weighted risk, clean risk of the two classifiers learned on noisy and clean data is equal. And in this setup, we were able to show that if you consider this combination of two loss functions and two hypothesis class, then only one of them leads to a positive result. That is, this is the case coming from here, that risk minimization under weighted 0-1 loss is not uniform noise robust. The next thing which we tried was alpha weighted gamma uneven margin squared loss, and this loss function did have a theoretical guarantee with linear class of loss function. Again, only linear class, not the whole class. So based on this, we tried two approaches. First was a loss function approach, where we said where we proved that this L alpha uneven squared loss defined like here, basically a weighted version of 1 minus alpha weighted version of square loss for positive class, and alpha weighted version of square loss for negative class, with a gamma imbalance parameter over here. So the interpretation here is the alpha would be user given and gamma would be tuned by the algorithm for imbalance. The good part about this approach is that the classifier can be obtained by just solving a linear system of equation, because if you solve for it, the result comes out to be just a linear system of equation, and there are high probability bounds available on the risk, like the high probability bounds explained earlier. This was one approach which was based on loss function. The other approach is a resampling based scheme. So here we considered alpha weighted uneven margin 0-1 loss. This is different from just alpha weighted version, because it has a gamma parameter over here. So because of this gamma parameter, the classifier changes. Now the classifier also has a gamma. The base classifier also has a gamma in the thresholding function. So this is the noisy cost sensitive base classifier, and now we want to learn f tilde, not f tilde, learn f star with the eta here. But the issues with using this loss function directly is that most algorithms use a threshold of 0.5, which will be different. Which is different from this, because we like earlier said that in cost sensitive learning alpha is different from half, and we can't use eta tilde for prediction because we are interested in clean data. So one proposed solution is to rebalance noisy data set with R star. And this R star comes from one of the famous results of Elkan, where he showed that if you have if where he basically showed that if you have an algorithm which uses thresholding of zero point 0.5 or p naught, but you want but the data which you have requires thresholding on p star, then this is a way, or this is a multiplier which you should use for downsampling the data, and then use p naught only directly. So basically a downsampling scheme which maps from p star to p naught, your threshold from p star to p naught. So once you have rebalanced the data, you can estimate this eta tilde b. And another thing to note here is that because it is a SLN setup, eta tilde b is would be same as eta tilde, because now it has been balanced. So this threshold would have been turned to half. So sine of eta tilde x minus 0.5 is same as sine of eta tilde eta x minus 0.5, because eta tilde x was a direct a linear function of eta in case of symmetric label noise, that is rho. So for a test point, the prediction is simply sine of eta tilde b x naught minus 0.5. So these two are the schemes which we had. One advantage over the existing schemes is that none of them requires estimating the noise rate or cross-validating over it, and there is an option of including the user given or the domain given alpha value or the cost value. So this was one aspect of learning away from 0-1 loss, that is cost sensitive learning. And recent work by Ren and group proposed that if you have, so what we considered was a situation where there were both imbalance and cost also, but Ren and group considered the case where there is noisy data and then there is only imbalance, not a requirement of explicit cost. So here, what they said was, let's reweigh the example based on the assumption that we have a validation set which is both clean and it is balanced also. So that's the architecture they have here. So they want to reduce the effect of training set biases, they call them, that is label noise or imbalance, and propose a meta learning algorithm. Again, like I said earlier, they assume availability of a clean and balanced validation set at every iteration. So if you see here, this is the forward noisy data which is being forwarded, and then these are the example weights, and after this it takes the backward pass from F. The weights are updated based on the the performance of these weights on the clean and balanced data set. So at the end of every iteration, the performance is measured, and then the weights, both these weights, that is the example weights, and the neural networks weights, are updated based on this, based on the performance of the network on this validation loss. Yeah. So next is we earlier, when we said that we'll use GANs, we used it in the convention. We used it in for our purpose of discriminative learning. But even when you use it for generative purposes, GAN, there is a chance that there could be your network could get affected by label noise. That's especially in the case of conditional GANs, which use the labels conditional GANs or auxiliary conditional GANs. These they use labels to generate the generate the data points, and hence are prone to label noise. So in this setup, one solution was provided by Thekkum and group. They proposed a robust conditional GAN, which basically modifies the generator, as you can see here, which it modifies the generator by a classifier H that is already learned on a certain hypothesis class and using certain loss function, further later on used as a regularized parameter. So, and there is a noisy channel here. So instead, this Y would be passed through a noisy channel again. So this, because in the conventional GAN, the real labels would be passed here. Here it is just a noisy channel that will be used to pass the labels. This was one work. The other another line of works for GANs and label noises by Kaneko and group. They also proposed a robust version of conditional GAN and auxiliary classifier GAN. Okay, sorry, I forgot. So in the RC GAN thing, they assume that the noise rate is so after a point they will require the noise rate estimate, the noise rate matrix. So they propose two algorithms. One is where they assume that it is known. In the other case, they estimated along with the generator's weights. So that's a point to note here. Yeah, and in this the RC GAN and RAC GAN, the noise transition model is used while training the discriminator. So the common generator across these is given in figure A, and then this is the baseline AC generator, that is auxiliary classifier generator, and this is the updated one. This is the one which they made as robust. So here there is a noise transition model which is fitted, that is this one. And again in this also, this is the noise transition model. So by noise transition model, it's just the estimated noise matrix. As you can see here, this is nothing but probability y tilde r given y hat r. So the flipping probability, again in this also, it's just the flipping probability. So this is for the GANs and label noise. Another interesting avenue in learning is positive unlabeled learning. This is particularly interesting because you only have in your data you only have positive labels, and then the rest of the data is unlabeled, and you can't even say that you can't assume that the unlabeled data is all negative, or you can't assume that it's going to be all positive. So an example would be a protein catalyzing a reaction would be a positive example, but say finding a negative example here is difficult. Similarly, a social media user liking a product is positive example. So these examples are reliable, so that's why you just use those positive examples. Now the label noise can occur in positive unlabeled learning or PU learning in two ways. First is either the data is noisy, that is the positive labeled data which you have has corruption in it, or the other way is you model a PU learning problem as a noisy label problem by labeling all the unlabeled examples as negative. So that is another way. So the first approach, where the first line of work where there is indeed noise in the positive labels, was dealt by Jan and group. They estimated, so they developed a probabilistic model, and then estimated the class priors, that is pi, and then in turn the posterior distribution eta, that is the in-class probabilities. And the good part about it is that it works well for density estimation, even in high dimensional data, because they are able to transform the full dimensional space to a univariate space. So they have this model alpha alpha positive class plus beta negative class, and then they learn these class priors where not alpha beta, alpha and 1 minus alpha. So they learn these alpha or pi in our case, these priors, and then later on the joint distribution, which can be further used for learning the posterior distribution. The other approach which I said was treat a PU learning problem as a label noise problem by labeling all unlabeled example as negative. So the novelty here lies in decomposing or discovering that the empirical risk when decomposed into positive and negative, the negative part is the only one which is going to affect, and you can indeed bound this negative part of the risk by one of the upper bounds provided by Patrinian group for Hinch laws, and that comes as an advantage because of using Hinch laws over there. Yeah, so this was another example of not conventional 0-1 learning or supervised learning. Some other situations where there could be interaction of label noise and other research areas. One is this active learning area or domain adaptation. And most recently, I saw like these two papers which particularly interested me. Was the existence of label noise in the while you are trying to get your classifiers to be fair, and the noise here is not in the conventional sense. It is majorly in the form of biases. Like the first case, due to human biases, you still have those protected attributes, and you still have those protected attributes, and it is possible that for those protected attributes your labels are flipped. Like only for certain group of people the labels could be flipped. The other interpretation or other version was a noisy version of unobserved variable is only available. So an example here would be that what is the so we assume, or there is an inherent notion that if a person has been arrested, that person would have committed the crime. But that's a noisy version. It's not. It is completely possible that he or she was falsely convicted. So this is these are some other label noise problems which are very interesting and have started to come up, especially the fairless literature part. These two appeared in AI Stats this year, I guess. So till now it was all learning, but there are some like logistical issues which one needs to take care, because label noise, you don't know whether, if you have real data sets like the ones from UCI, you know that they have been developed properly and they have been checked for properly, so the chances of noise there would be like very less, unless you actually get the images or data from internet, like internet scrolling or something of that kind. So now how do you design experiments, or how do you evaluate those experiments for training or get the data which is noisy for training? So there are two ways like one can do it. Is first is this synthetic database, where the data can be generated in a certain way, and then noise is induced by flipping the labels. So this particular example shows that originally this is a synthetic data case. This was the data was generated in this form. Black is positive class, red is negative class, and then they are not linearly separable. A quadratic classifier would be required to separate them. Now when 60% noise of 60 or 70% noise these labels are flipped with this percentage of noise, then you get this situation that it is completely mixed. So, so your classifier can, a classifier which you are learning could probably just draw a classifier here. It's really difficult. So you would ideally want your classifier to do this and not this. So this is a good example or good way of evaluating your classifiers when you're designing these label noise learning algorithms and want to actually check how they are performing. Another one which came up is this clothing 1 million data set. It is a huge data set, and since these images were scrolled from the internet, there is a very high chance, or like at least the authors or the researchers have been using this data sets recently quite often to demonstrate the performance of the proposed algorithms or the improvements they suggest. So this was all about label noise, but what ahead? There is this notion of categorical feature noise. So by categorical feature noise, I mean that generally if you see feature vectors, if they are continuous, adding a noise in continuous variables would be considered as you add a Gaussian noise there, so it won't affect much. The classifier won't get affected much, because if you try to imagine or picturize your data in 2D, and the value of X won't change if you just add a small amount of noise to your feature. The value of X won't change, and hence its effect on the classifier won't be that much, because the distance, the location of the feature vector did not change much. But if you consider a situation where the feature vectors are not continuous but of binary type, and there is noise. So in binary type, if you say that there is noise, would mean that they have been flipped. Again, like label noise, they have been flipped. So some examples would be that there is a room with many sensors that are connected in series, or with individual battery which is measuring temperature, humidity, and that's a high or low value. So if one of them fails, the whole series or the whole thing is going to fail, and your final the final sensor value which you would be getting from there could be erroneous. Similarly, a power failure or battery failures will lead to all our individual sensors or attributes providing noisy information with same or different probability. So recently, Petzeti and group presented or developed two noise models which are appropriate for categorical feature noise. That one is of the type 1 here, that is the sensor example, where the probability of flipping for all the elements of a feature is same, and the other is the power failure example, where the probability of flipping for each element of the feature vector or each attribute, each feature is different. So as I said earlier, that the flipping of these values can alter the classifier. So in these two models, the authors were able to show that if you use squared loss with linear classifiers, this particular model where the flipping probability is same for all feature values, then it is robust, and you can obtain the classifier, a good classifier, even when learning from noisy data. But then there are counter examples for 0-1 loss in this setup and in this setup, in both of these setups. So this is one area which I feel could revive again, because I saw a couple of more papers where people are actually trying to trying to understand feature noise, not in the categorical setup, but in the general setup. But this could be another thing which could come up, So, so yeah, that's all we have. And now these are some of the references, and we'll be happy to share the slides. If there are any questions, we'll be happy to take it.
Yeah, definitely.
Yeah, it's a quiet audience. Hey, this is Tim again. So again, people can feel free to just unmute themselves and speak up or drop questions in the chat if there are any.
In addition to whatever we presented, there is a huge literature out there. I had a list, but because of, again, time constraint or not being able to do enough justice to the work, I can like restricted myself to not include all of them. But there is a lot, and we can like point to the literature if anyone is interested.
Okay. Well, I'm not hearing any questions right now. I think we all appreciate you taking the time out to present the tutorial. It was an amazing amount of information packed in those slides, so that was great. And we have the recording that's going to be posted. And was your contact information in the presentation anywhere? I mean, I know it's online, but
Yeah,
did you have your
there.
email?
Yeah, it's
Okay,
it's
good.
there.
Right. So then, people can feel free to reach out to you by email and follow up with any questions that they might have.
Okay.
Yeah.
Okay, awesome. All right. Well, thank you very much. I'm actually going to pause the recording, but people can feel free to hang out and see if you have additional questions. But again, thank you very much. Great presentation. We appreciate you taking the time to put that together and to deliver it.
Thank you to the organizers also for letting us, giving the opportunity to actually present it and then coordinating it so well.
Yeah.
Yeah.
Thanks to both of you for coordinating it and hosting it. And of course, audience, yeah, I mean, it is past midnight, 2:30 onwards in India time, and only I can see two people from India as far as I know, Gangadhar and Prafula Kumari. Thanks to both of them.
Thank you both.
Oh, sorry. Hey, this is Tim again. Sorry. Who's the host now? I was going to pause the recording, but it looks like I'm no longer the host. Or one of you guys?
Yeah, team. I'm a host. I will post the recording.
Okay. Can you just, you have to stop it. Apparently I can't now.